Hey there, hi there, ho there, welcome back. Let's talk about geologic time. It's just so hard for us to wrap our brains around how much time has passed, how much time Earth has existed for, the solar system has existed for, the galaxy, the universe has existed for. A lot of stuff has happened in that time that Earth has existed. One of the greatest illustrations of geologic time and the processes through time is, of course, the Grand Canyon. It's the grandest of the canyon of them all. If you've ever had a chance, if you ever have a chance, make sure to check it out. You know, I went as a kid. Whatever. It's a hole in the ground. But as an adult, it's a little bit different experience. Go during the colder months. Much less people. It's a lot nicer. It can get hot in the summer, especially if you go down to the bottom. If you do go down to the bottom, prepare. Anyway, the Grand Canyon, there's over 1 billion years of geologic history as we kind of go down through the layers in the canyon. It tells a story of mountain building, oceans coming into what is now Arizona and leaving, weathering and erosion, the process of breaking down material, ancient life with all the fossils. The Grand Canyon tells a hell of a good story. And we know these things by applying what are known as principles of relative dating, which we'll get to recognize that present-day processes, what we see now, have operated throughout Earth's history, this uniformitarianism. So let's break this down, all right? So we're obsessed with time. I never have enough time, and we organize our life around time. I got to do this, I got to do that, I got to schedule this. For humans, right, our common time units, seconds, minutes, hours, up even to years and decades, right? However, ancient history involves hundreds of years or thousands of years, and we can wrap our brains around that, like, the Egyptian dynasty, that happened, thousands of years ago. We can kind of wrap our brain around that. But geologic time involves millions and even billions of years. It's hard to grasp. So, with geologic time, geologists, we actually use two different frames of reference when discussing geologic time. We look at something called relative dating, which kind of puts events in a sequential order, and relative dating is basically saying this happened before that, or this happened after that. Relative to this thing is older, this thing is younger. We're not putting like a specific number on it, like, oh, this happened 300 million years ago. We're just saying, oh, this happened, then this happened. Relative to one another, this happened first, this happened second. So that's relative dating. But then we also use absolute dating, which is putting a specific kind of number, or at least a little bit of a time frame on a particular event. So absolute dating is putting a number to it. So with relative dating, we've been able to kind of establish what's known as the geologic time scale, which I've talked about in other units. But we've used relative dating principles to establish a relative compared to this and that geologic time scale based on geologic events and biologic events. So we can kind of, fish happened, and then plants happened, then amphibians, and then reptiles. So we understood kind of the order of things. So that's relative dating. We weren't putting a number to it. We were just kind of putting things in order. Then we started to break down this time scale into eons, eras, periods, and epochs. Absolute dating, to put numbers to these things, really didn't come around until we understood the principles of radioactivity and began radiometric dating. More on that in a later section. But that's the most common way of obtaining absolute ages, numerical ages of rocks. Some fancy machinery, very expensive fancy machinery that helps us do just those things. And the way we do that is we look at the decay rates of various naturally radioactive elements present, even in very, 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 very small amounts in some rocks. Not all rocks, but in some rocks. And again, the discovery of radioactivity in the late 1800s, early 1900s allowed us to do that, to kind of come up with this method, come up with these machines, and helped us put some numerical, values to things. That's absolute dating, putting numbers to it. So then we can kind of match those two things together. So the geologic time scale is a dual scale, and it shows both a relative scale and an absolute scale. So we can talk about events that have occurred, and now we can put kind of a time frame of when those fit in. we didn't always know how old the Earth was. In fact, the Earth being about 4.5, give or take, billion years old, we really didn't know about until, again, radioactivity was discovered, radiometric dating became a thing, and we really didn't know how old the Earth was specifically until about the 1950s. So there's a little bit of a journey to get there. And the concept of geologic time has changed throughout human history. Early on, the age of the Earth was based on early Christian theologians kind of studying the Bible. So there was one gentleman, James Ussher, calculated the age of Earth based on Old Testament genealogy, looking back, starting with Adam and Eve, if you know the story of the Bible, and then, they begot this, they begot that, they had this kid, they had that kid, and kind of going backwards throughout the Bible. He came up with a very specific date that the Earth was created on October 22nd, 4004 BC. So, that's very specific. I don't know how you got that, but you use the Bible to come up with that. So for almost 100 years, that was about the answer. So that's 4000 BC plus another 1600 or so. So for nearly a century, it's considered heresy, anti-religion, against the law to say Earth was any older than 6,000 years. So for about 100 years, 6,000 years, that's how old the Earth was. Then the scientific revolution occurred in the late 17th century, early 18th century. And then Earth's age. So then fast forward to the 1700s to the 1800s, Earth age was started to become estimated scientifically. Georges Louis de Buffon in the 1700s calculated, how long Earth took to cool gradually from a molten beginning. So it started the understanding, Earth had to start from a molten beginning. And so what he did was used hot liquid iron balls, melted, heated them up so they're pretty much melted, and then various diameters, and then figure out how long it took for those things to cool. So extrapolating the cooling rates to, he imagined a ball the size of Earth, he calculated Earth would be at least 75,000 years old. So, all right, so now we're looking finally past 6,000. Still short of the 4.5 billion that we know it is now, but at least we're getting past, 6,000. And there was a number of these estimates. Others used different techniques. Some scholars used rates of deposition of sediments and the total thickness of sediment in the crust, and that got us estimates of a million to more than 2 billion years. So a big range, but again, at least we're getting there. A gentleman by the name of John Jolly, in 1889, used the amount of salt carried by rivers when weathering and erosion occurs on the surface, and that material makes its way into rivers, and those rivers eventually flow into the ocean, and looking at the salinity of salt water and how long it would take to get the ocean that salty based on the salinity in rivers, how much salt rivers bring to the ocean, he obtained a minimum age of 90 million years. Again, far short than 4.5 billion, but at least we're putting it out there. Then we got Lord Kelvin. If you've ever taken a chemistry or physics class, the Kelvin degree scale, that's this guy. He knew about high temperatures deep inside mines. The further you go down, if you ever go into a mine, like people think, oh, it's cold in there. Well, yeah, initially, but the further you go down in the earth, actually, the hotter it gets. So he knew about high temperatures inside deep mines and the reason that Earth was losing heat from the interior. And so assuming Earth was once molten, kind of like what the Buffon guy was doing, he used the melting temperature of rocks the size of Earth and the rate of heat loss to calculate the age of Earth between 20 and 400 million years old. Again, a big range, but at least we're putting it out there. But the issue is that this age was too young for the geologic processes that we now started seeing by geologists at the time. As we get into the late 1800s and early 1900s and a better understanding of different geologic features and how they occur, that's just not enough time to explain what we see. That's just not enough time. 20 million years isn't enough time to explain what we're seeing in the Grand Canyon. So that started to lead to a crisis in geology. How can these things happen in this short amount of time? Something's not right. Something's not working out. So because of that, people are like, oh, see, that's why the Earth is only 6,000 years old. But no, all of this can't happen in 6,000 years. But we're getting all of these ages that are just seem even too short. Even 400 million seems too short. But what Kelvin didn't know about was radioactivity as a source of heat energy within the Earth. So more on that in a little bit. But all these people, at least they were putting these things maybe in the millions of years, even up to 2 billion years, but it took some time till we figured out the absolute age of the Earth. Okay, so that's just a brief history of geologic time. Before we go, let me give you the only number in the code and the super secret code, and that is the number 7. You got me? The number 7. One more time, number 7. It's the only number in the code. So we'll pause here. When we come back, so there's a little bit of the history of geologic time. We'll focus on relative dating, what it kind of tells us, how we got there. I'll see you back here in just a second.